So these two files, go ahead and take these files, download them. Just take note, these are licensed to Intel, so make sure you understand the license before you go using these, commercially and stuff. So take these two cascades, download them, put them in your, and to download them, you can just go to raw, right click, save as, okay? Save them to where you're working, both of these, and then you're ready to go. And here I'm going to show you how they work. So to start, you're going to want to have NumPy as NP and CV2 imported. And now we're going to define the two cascades. We're going to have a face cascade equals, and this will just be the loading of that cascade. So it'll be cv2.cascade classifier, and then we load in that cascade, which was har.
What's up, everyone? Welcome to part one of a data set, but instead of handwritten link to where you can get fashion MNIST from Kaggle.
Hello world, it's Siraj, and the question I get asked the most by far is how do I get started with deep learning? And it makes sense to ask that. There are so many different learning paths and tools you could use. It's hard to just pick one and roll with it. In this video, I'm going to explain why you should use a deep learning library called Keras to build your first deep neural networks and compare it to other options. Then we'll use Keras to build an app that generates text in the style of any given author. Deep learning only started getting really popular a couple years ago when Hinton's team submitted a model that blew away the competition for the large-scale visual recognition challenge. Their deep neural network was significantly better than all benchmarks. Illuminati confirmed. Because it used lots of GPU computation and data, others began to take notice and implemented their own deep neural networks for different tasks, resulting in a deep learning renaissance. Deep learning played a huge part in the biggest AI success story of 2017, AlphaGo, Google's algorithm that mastered the game of Go, previously thought near impossible. Similar improvements were made in fields like vision, text, and speech recognition. WaveNet, for example, was a model that massively sped up improvements to speech to text and text to speech, resulting in lifelike generated audio. Theano was really the first widely adopted deep learning library. It was maintained by the University of Montreal, but in September of last year, they announced that they would stop developing for Theano in 2018. Yes! Different open source Python deep learning frameworks have been introduced the past couple of years, and some got lots of traction. As of now, TensorFlow seems to be the most used deep learning library based on the number of GitHub stars and forks, as well as Stack Overflow activity. But there are other libraries that are growing passionate user bases as well. PyTorch is a great example. It was introduced in January 2017 by Facebook. They basically ported the popular Torch framework, which was written in Lua, to Python. The main driver behind PyTorch's popularity was the fact that it used dynamic computation graphs. That means they are defined by run instead of the traditional define and run. When inputs can vary, like if we're using unstructured data with text, this is super useful and efficient. When it comes to static graphs, we first draw the graph, then inject the data to run it, That's define and run. For dynamic graphs, the graph is defined on the fly via the forward computation of the data. That's defined by run. But in addition to TensorFlow's main framework, several companion libraries were released, including TensorFlow Fold for dynamic computation graphs and TensorFlow Transform for data input pipelines. The TensorFlow team also announced a new eager execution mode, which works similar to PyTorch's dynamic computation graphs. But wait, other tech giants have also been getting in on the game. Microsoft launched its cognitive toolkit last year. Facebook launched Caffe 2. Amazon launched MXNet. DeepMind released Sonnet. There's also Deep Learning 4J, DLive, H2O.ai, and Spark. Oh, and Facebook and Microsoft announced the Onyx open format to share deep learning models across frameworks. For example, you can train your model in one framework, but then serve it in production in another one. I know. Deep AF overload. But look, the best way to learn how some AI concept works is to start building it and figure it out as you go. And the best way to do that is by first using a high-level library called Keras. Keras is effectively an interface that wraps multiple frameworks. You can use it as an interface to TensorFlow, Theano, or CNTK. It works the same no matter what backend you use. Francois Chollet, a deep learning researcher at Google, created it and maintains it. Last year, Google announced it was chosen as the official high-level API of TensorFlow. When it comes to writing and debugging custom modules and layers, PyTorch is the faster option, while Keras is definitely the fastest track when you need to quickly train and test a model built from standard layers. Using Keras, the pipeline for building a deep network looks like this. You define it, compile it, fit it, evaluate it, and then use it to make predictions. Consider a simple three-layer neural network with an input layer, hidden layer, and output layer. Each of these layers is just a matrix operation. Input times weight, add a bias, and activate the result. Repeat that twice and get a prediction. Deep networks have multiple layers. They can have 3, 4, 5, whatever. That's why they're called deep. And these layers don't have to use just one type of operation. There are all sorts of layers out there for different types of networks. Convolutional layers, dropout layers, recurrent layers, the list goes on. But the basic idea of a deep neural network is applying a series of math operations in order to some input data. Each layer represents a different operation that then passes the result onto the next layer. So in a way, we can think of these layers as building blocks. If we can list out all the different types of layers, we can wrap them into their own classes and then reuse them as modular building blocks. That's exactly what Keras does. It also abstracts away a lot of the magic numbers you'd have to input into a deep network, written in, say, pure TensorFlow. When we define a network, they're defined as a sequence of layers using the sequential class. Once we create an instance of the sequential class, we can add new layers where each new line is a new layer. We could do this in just 2 steps, or we could do this in 1 step by creating an array of layers beforehand and pasting it to the constructor of the sequential model. The first layer in the network must define the number of inputs to accept, depending on the, for example, are things that we can decide. This is the art of deep learning. Once the network is compiled, it can be fit. Network. The optimization algorithm we use to evaluate it are things that we can decide. This is the art of deep learning. Once the network is compiled, it can be fit, which means adapting the weights on a training data set. Fitting the network requires the training data to be specified, both a matrix of input patterns X and an array of matching output patterns Y. The network is trained using the backpropagation algorithm and optimized according to the optimization algorithm and loss function specified when compiling the model. Finally, once we are satisfied with the performance of our fit model, we can use it to make predictions on new data. This is as easy as calling the predict function on the model with an array of new input patterns. For our text generation sample, we'll see that it generates text in the style of our favorite author just as we fed it in. 3 points to remember. There are lots of new competitors that showed up in 2017 for deep learning libraries, but Keras is still the easiest way to get started. PyTorch is getting really popular and is the best way to build models next to Keras. And deep networks are a series of math operations in the form of layers. Just mix and match them to get different results every time. The coding challenge winner from the War Robots video is Alberto Garces. He used the proximal policy optimization algorithm to train an AI to balance a pendulum using the OpenAI gym environment. Top-notch work, Alberto. And the runner-up is Sven Niederberger, who landed a simulated SpaceX rocket using PPO. Such a cool use case. This week's coding challenge
their relative locations, their size. It may even know some extra information. There's a book sitting in the background. And if you want to build a system on top of computer vision, say a self-driving vehicle or a robotic system, this is the kind of information that you want. You want something so that you can interact with the physical world. Now, when I started working on object detection, it took 20 seconds to process a single image. And to get a feel for why speed is so important in this domain, here's an example of an object detector that takes 2 seconds to process an image. So this is 10 times faster than the 20 seconds per image detector. And you can see that by the time it makes predictions, the entire state of the world has changed. And this wouldn't be very useful for an application. If we speed this up by another factor of 10, this is a detector running at 5 frames per second. This is a lot better. But for example, if there's any significant movement, I wouldn't want a system like this driving my car. This is our detection system running in real time on my laptop. So it smoothly tracks me as I move around the frame, and it's robust to a wide variety of changes in size, pose, forward, backward. This is great. This is what we really need if we're going to build systems on top of computer vision. So in just a few years, we've gone from 20 seconds per image to 20 milliseconds per image, 1,000 times faster. How did we get there? Well, in the past, object detection systems would take an image like this and split it into a bunch of regions, and then run a classifier on each of these regions. And high scores for that classifier would be considered detections in the image. But this involved running a classifier thousands of times over an image, thousands of neural network evaluations to produce detection. Instead, we trained a single network to do all of detection for us. It produces all of the bounding boxes and class probabilities simultaneously. With our system, instead of looking at an image thousands of times to produce detection, you only look once. And that's why we call it the YOLO method of object detection. So with this speed, we're not just limited to images. We can process video in real time. And now, instead of just seeing that cat and dog, we can see them move around and interact with each other. This is a detector that we trained on 80 different classes in Microsoft's COCO dataset. It has all sorts of things like spoon and fork, bowl, common objects like that. It has a variety of more exotic things, animals, cars, zebras, giraffes. And now we're going to do something fun. We're just going to go out into the audience and see what kind of things we can detect. Does anyone want a stuffed animal? There's some teddy bears out there. And we can turn down our threshold for detection a little bit so we can find more of you guys out in the audience. Let's see if we can get these stop signs. We find some backpacks. Let's just zoom in a little bit. And this is great. And all of the processing is happening in real time on the laptop. And it's important to remember that this is a general purpose object detection system. So we can train this for any image domain. The same code that we use to find stop signs or pedestrians, bicycles in a self-driving vehicle can be used to find cancer cells in a tissue biopsy. And there are researchers around the globe already using this technology for advances in things like medicine, robotics. This morning I read a paper where they were taking a census of animals in Nairobi National Park with YOLO as part of this detection system. And that's because Darknet is open source and in the public domain, free for anyone to use. But we wanted to make detection even more accessible and usable. So through a combination of model optimization, network binarization and approximation, we actually have object detection running on a phone. And I'm really excited because now we have a pretty powerful solution to this low-level computer vision problem, and anyone can take it and build something with it. So now the rest is up to all of you and people around the world with access to this software, and I can't wait to see what people will build with this technology. Thank you.
Python's where it's at. You can do almost anything with it. You know, you should take this online Python bootcamp course on Udemy. It's taught by an expert instructor who's also a data scientist. You'll learn how to automate tasks, create games, and even apply it to real-world problems, all for the cost of takeout. The course is yours to keep and take at any time. And if it doesn't work out, you can get your money back in 30 days. I can't wait to see what you do with this. Get started now with a special discount.
This is Cosmo.
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 Cosmo is a rambunctious little kid.
A little bit mischievous.
He's smart.
A lot of robot in a very small package.
All the technology inside of Cosmo is really there for one reason, to bring the magic of robotic character to life.
It's a very complex system and has 4 transmissions inside of it with probably 40 or 50 gears.
Each robot is made out of over 300 different parts.
There's the AI systems,
The robotics,
accelerometers,
the animation,
gyros,
the computer vision. We're running an extremely complicated artificial intelligence inside the robot, which needs to make thousands and thousands of decisions per second.
He's a mobile manipulator. He can drive around the world. He can see you. He can recognize you.
He looked up at me and his eyes went, whoa. And I was like, whoa, he just recognized me.
Gives you goosebumps because you realize that this is a little character who actually understands who you are and what role you play in his world.
Figuring out the path to a unique personality it's an ongoing question.
I think we did about 40, 50 studies on just little nuances, looking at the interface with the monitor.